Okay, the next speaker of this session is Ahmed Shalabi, and he's going to talk about space-time curvature from ultra-rapid measurements of quantum fields. And Ahmed, I'm going to give you 12 minutes for the talk, and then I'll give you a warning 2 minutes before the end of the talk. So whenever you're ready, the floor is yours.
Perfect. Thank you so much. And just before beginning, I wanted to thank all the organizers for the opportunity to speak at the conference. So this work was done with collaboration with Rick Perch at the University of Waterloo. And let's just jump right into it. So this work is a contribution to basically a line of thinking about rephrasing the geometry of spacetime in terms of observable quantities of quantum fields. And the motivation behind that would be that the classical notions of distance and time, rulers and clocks that we know and love from general relativity start failing as you approach the high energy Planck scale. So the big picture here, the thing that we are addressing is we're asking the question, can we use particle detectors to probe the effect of curvature on quantum field in such a way that we are able to locally reconstruct the background geometry that the field lives on. So first step would be to introduce the particle detector model. So we've seen the linear under-DeWitt model time and time again in these talks. So just quickly summarize it. It's a two-level system. And the only thing I wanted to highlight here is, since we are going to be working on an arbitrarily curved background, instead of prescribing an interaction Hamiltonian, we'll prescribe an interaction Hamiltonian density, where chi is the switching function that dictates the strength and duration of the interaction. F of x is the shape or the geometry of the detector itself, and mu hat is the detector monopole moment in the interaction picture. So next step would be to construct the time evolution operator, which is given by this. And the idea here, since we have a Hamiltonian density, we've built this whole thing to be covariant and will be integrated over the entire manifold or a region of the spacetime. The typical approach from here would be to approach this problem perturbatively, but instead what we do here is use delta coupling, which is just intuitively, we're going to turn on the interaction for a time scale that is much shorter than any of the relevant length or energy scales of the internal dynamics of the detectors. And the first thing that we did in the paper, we showed that the time evolution operator can be written analytically in terms of these y hat operators, which are basically just smeared versions of the field operator with respect to a test function f that corresponds to the shape of the detector that we've coupled with the field. We're going to assume that the detector starts in a ground state and that the field's in a given Hadamard state. Then we go and show in the paper by evolving the joint field and detector state using the time evolution operator that we've just seen, taking the expectation values, and then tracing out the field degrees of freedom post interaction to arrive at this expression for the transition probability of the detector. And then finally, we show, since if the field's in a Hadamard state, then that means it's a quasi-free state whose endpoint correlators vanish, or odd endpoint correlators vanish. So we're able to show that the expectation value is just given by the exponential of -2 mathcal L, where this mathcal L term is given by this. And then we can plug this in to give us a general expression for the transition probability P for particle detector delta coupling on any kind of background spacetime. Just a couple of things to highlight here. First of all, that this expression is a direct generalization of the flat space version or the flat space response, where the flat space version wouldn't have obviously the determinants and wouldn't have the flat space Wightman. And it's also important to note that the point length limit is well defined. This term blows up slower than the exponential. This whole thing gets suppressed, and we're left with the transition probability of 1/2, because we end up with a maximally mixed state for the detector, and this becomes important later. So what we're effectively trying to do here is write the transition probability as its flat space counterpart plus corrections due to curvature. So since we assume that the field is in quasi-free state, then we begin with this basically an expression or approximation for the Wightman function locally, where this is the Van Vleck determinant. The V and W functions are regular functions. V corresponds, or V can be fully determined by the background spacetime properties of the field, and W is state dependent. So this computation is a bit too long, so I will just kind of try to motivate some of the steps, hit on like certain milestones instead of obviously outlining the whole thing. So we begin by factoring the flat space Wightman function, and we'll expand V and W in powers of sigma, the Singe-Rolle function, giving us the following expression. Then it was shown that the expansion of the basically state-dependent terms can be written as this. And then we also utilize this following expansion for the Van Vleck determinant. We bring this all together, we combine it to arrive at this approximate expression for the Wightman function, this arbitrary Wightman function in terms of the flat Wightman function, plus all these corrections due to curvature. Finally, we expand the state-dependent terms in locally around the center of the interaction. So if the particle detector is on a trajectory z of tau, then we effectively, what we're trying to do is just evaluate the tensors, all these curvature tensors from the center of the trajectory or the center of the interaction, which gives us the following approximate expression for the Wightman function in terms of corrections to the flat space version. The final piece that we need is just the Jacobian in the expression for MathCal L. Since we're working locally, we choose to operate in Fermi normal coordinates. And then we show that this expansion for the determinant of the metric, that the expansion is given by this, where the Mij tensor is defined in terms of these components of the Riemann and Ricci tensors, giving us the expression, which is effectively what we wanted, that the transition probability on any curved background is the flat space plus corrections due to curvature, where these corrections are given by the following terms. So, for example, this term corresponds to corrections due to the volume element locally. This correction corresponds to a change in the rest frame or the shape of the detector in its rest frame due to its potential acceleration. We've got the state-dependent term, and then we've got corrections due to curvature. So now the second part of the talk, we will address the idea of recovering the local geometry by fully reconstructing the Riemann tensor from the equation above. So the idea in a nutshell is basically just saying, okay, we will pick a detector geometry and we're going to put it on some trajectory. We will probe the curvature along each direction by coupling the detector with the field state. And then since we've figured out that the point-like limit of the transition probability would be a half when we're doing delta coupling. So what we're looking for effectively is giving a shape. And once we can gain any information about the field through a non-exactly a half transition probability, so that the detector would have a finite span in space-time, we'll take that transition probability, we'll take the size, and then compute all those terms in the expression or the expansion above, or in terms of corrections of curvature. And from there, we would be able to obtain the curvature tensors, Mij, Rij, and R from the calculations that we've done and the transition probability. So we'll make a few a priori assumptions that the spacetime is locally stationary and that the field remains approximately in the same quasi-free state. We are going to assume that the detectors are Gaussian in their Fermi normal coordinates. This is basically just a generalization of the circularly symmetric Gaussian into Gaussians that are elliptical, so we can smear them along any of the spatial directions. And then we show in the paper that with this choice, we can compute all those terms analytically. The LR term has to be computed numerically, and moreover, the term that corresponds to acceleration is strictly 0. That allows us to simplify our corrections due to curvature like this, where Mij is the tensor that we've seen before, and Nij is this other tensor. I'll not be able to get into a lot of detail, obviously, but the most important thing to know, the thing that this really hinges on, is that all those terms are linearly independent. So they can be varied independently, allowing us a fully unique reconstruction of the metric tensor, of the Riemann tensor. And then from those, we show that we could recover all those specific components of the Ricci and Riemann tensors, and obviously recover the state-dependent term. Now, in principle, if the spacetime had any kind of symmetry, that in principle would be enough. But since we are working generally, we can only recover in 3 plus 1, we can only recover 13 independent terms of the curvature tensors. But just to keep it short, we also show in the paper how one could basically consider different states of motion of the detector, such that we can access the terms in the Riemann tensor that we were not able to access from the initial coupling in terms of other components that we've already calculated. And with that, I would just like to conclude and discuss some outlooks for potential work. We've kind of motivated the problem in terms of formulating these geometric properties of space-time in terms of measurable properties or measurable things about quantum fields. But there's also a low-hanging fruit where we discuss the inverse problem. More often than not, one in RQI would know the geometry and not the Wightman function. And I think another interesting direction to take this is repeating the analysis perturbatively or for other kinds of switches, for other kinds of couplings like nonlinear or derivative coupling. And with that, I am done. Thank you so much.
Thank you so much, Ahmed, for the talk. And I'd like to, I guess we have time for a quick question. Does anyone have a question? Well, Ahmed, if you can stay until the end of the session. Oh, there's a question. Morgan, go ahead.
Please go ahead.
Okay, so this is actually really interesting. My first question, I guess, was how come the acceleration term vanishes? Is it, are you considering that a trajectory of 0 acceleration, but like why is, because that's, I guess, like a kind of a typical curved spacetime Unruh effect there.
Right, so the idea is not that the acceleration vanishes, it's just simply you lose whatever information that the acceleration would give you if you were to use a Gaussian detector. So it's not to say that the acceleration doesn't matter, it's just the you don't have access to that information if you're using specifically a Gaussian detector.
Interesting. Okay. And then do you get, so you have the transition probability, but do you get any notion of temperature that you can extract from that? Because you got, well, I guess there's no acceleration there, but there should be temperatures associated with curvature and things like this. Are you able to get some information from that out of there?
In principle, I don't see why not, but that's not something that we've considered. I think you could repeat this kind of analysis where you assume that the field starts in a KMS state and see what happened. That'd be actually very interesting to see. But we didn't really look at Unruh effects of temperatures.
Maybe if the chair allows me, I'll talk with you.
All right. If the chair allows me, just one quick comment. I don't think, Ahmed, that a Gaussian detector would not see the acceleration. I think the fact is that you're doing a delta switching, right?
Mm-hmm.
If you're doing a delta switching, you're not going to see acceleration effects.
Right. So that's also a great point. Because my understanding of it
certainly sees the Unruh effect too, or well, acceleration effects for sure.
Mm-hmm.
Okay.
Mm-hmm.
And delta switching, you're doing one point in time. It's like being inertial, if you want.
Yeah, I see. Okay. Cool. Really nice, actually. Really cool.
Thank you so much. Thank you so much.
So we can still continue the discussion later if you can stay into the end. So let's thank Ahmed